heartily apologize from my side as of some technical issues, right? And my system got crashed, right? Okay, so still things are going on, right? I'm trying to replace the part that is actually making up some disturbance in my process, right? So for that reason, teaser was not there, right? Again, heartily apologize from my side, but you have shown your support to me from all sides in all situations, right? So today also, yes, come on, show your love and support to this entire channel and this session. Again, apologize from my side, right, for this. Hope so I have contributed. The initiative of teaser, right, was kept for you all, but this time I tried a lot, but every time, right, there was an technical issue arising and my system didn't supported me. Still, I am trying to find a fault, right, so that it can be recovered into the very short amount of the time, and again we will back, right, with the awesome teasers, right? Hope so, right? Sorry, yes, you all are going to show, right, supports towards us. Okay, so guys, hello bacho, Sat Shri Akal and Namaste from my side. Your own physics educator Indrajeet Singh, right, welcoming you all onto the most sensible platform, right, for an aspirants, those who are preparing for JEE, NEET kind of examinations, right? You requested, we kept our promise. You said you are in the need of a crash course. We introduced the Champions series. It started with units and measurements, followed by motion in 1D, 2D, NLM, right? And then we moved on to the work energy and power, rotational motion. We saw concepts of gravitation, solids, fluids, right? And a very different domain, heat transfer and thermodynamics. And after that, finally, we have reached to an edge. 2 sessions of the physics, right, are remaining on the 11th syllabus, and obviously 2 sessions of the 12th syllabus are remaining. Okay, SHM and waves. Obviously, SHM and waves, right, both together holds, right, a high weightage into the syllabus of the JEE and NEET. But it's okay. Lots of small things are there in both of the chapters, and it is important, right, okay, to study them individually. So I thought it is good to have a session, an individual session on each chapter, right, so that each and every part and of this thing, right, of this syllabus should be covered in detail, right? And lots of shortcuts we are going to see today. So guys, stay till end, right? Stay till end. Okay guys, so today we are moving on to the concepts of SHM. As per our tradition, let's move on to the part. We are going to see the concepts of what actually the periodic motion is. Actually, SHM is a spatial category, it is included, right? It's a part of a spatial category of a motion, right? But you can understand why it is spatial, why it is different from another motions, right? Another type of motion, right? Why? Lots of things are there. We are going to discuss in detail, and lots of visualizations are going to come. So those students who are going to see this lecture till end, I must say you are going to enjoy the each and every moment of it. Stay till end. Okay? Some of the concepts of the oscillatory motion, fundamentals of the SHM. We are going to see the most important, the comparison of the SHM with the uniform circular motion, right, by the Phasor method. Time period cases of SHM, some of the cases of the angular SHM, and most of the important damping and the forced oscillations, right? Damping and the forced oscillations. So are you all ready? Right? Yes, I think you all are ready. So now let's move on to the next part. Okay, as per our tradition, first of all, let's move on, right, to the flowchart of SHM. right? The concept of SHM, right? Okay, it's see, first of all, SHM stands for Simple Harmonic Motion, right? The first part of the Simple Harmonic Motion, right, goes to periodic motion, right? In periodic motion, we are having a different category, right? Oscillatory motion. In oscillatory motion, right? And then it moves on to the concepts of SHM, right? So first of all, we are going to see, right, how different the oscillatory motion is, right, from periodic, how different the SHM is from oscillatory and periodic, right? And how this entire category is different from whatever, right? This entire category is different from the motions that we have studied till now. Okay, so now the second part of the SHM, right, it moves on, right, to the fundamentals of SHM, right? Okay, to the acceleration and velocity relation, right? To the graphs of SHM, right? Okay, and finally, right, some important things are first okay, energy in SHM. The third part of an SHM directly move forward, right, toward the time period of an SHM, in which there are some spring cases and there are some spatial cases, right, and the relevant formulas. Okay, after that, the last part directly moves on to the concepts of angular SHM. When the angular SHM, right, the cases of the conical pendulum. After the cases of the conical pendulum, we are having some rigid body pendulum cases, right? Okay, and some of the calculations of the restoring torque. And the last part is damping and forced oscillations, right? Damping and forced oscillation, right? So this is what the entire thing, right, of SHM is all about. Okay, so now let's start with the main content. Yes, today we are going to deliver the thing into the quite different way. Lots of visualizations are going to come, and obviously we are going to compare the SHM with our day-to-day life also, right? Okay, so you have to just stay till, and I must say lots of funny examples are going to come and you are going to enjoy. Come on, let's start with, okay, the periodic motion. First of all, if I'm talking about the periodic motion, then I must say it is a spatial category of motion. Sir, you said it is a spatial category of motion, but you should explain, right, how it is different from others, right? How it is different from others. It's a very important thing, right? I must say it, yes, it is a spatial category of the motion, but how it is different from others, I must say, right? What is an actual difference between this and all? So I want to tell you all that we are a common man. Let's take a day-to-day life example there. Okay, we are a common man. We are living in a town. Some might be living into the cities, some might be living into the metropolitan cities, right? We are the common peoples, right? Even who is a millionaire, he is also a common people because he is having, right, he is following his regular routine, right? Okay, regular routine you all are aware of, right? So we are common peoples, right? We are living our life happily, right? Okay, some pros and cons are the part of the life. It's not a big deal. We are living our life happily, but who are protecting us? If I'm talking at the regional level or at the state level, we are having the armed forces, that is police, right? If I'm talking about then international borders, right, we are having our own army. So what is different between us and them? Right, we are the common people, right? Now right? We are the common people, the one who are protecting us at the regional or the state level, they are a police. And those who are protecting us at the international borders, they are our army. They are also the common people. They are also having their own routine. But what is an actual difference between them and us? Right? You can understand it. Can I consider those who are protecting us at the regional and the state level and those who are protecting us at the international borders at the special category of the humans? Our commandos, those who are working, those who are protecting us at the international borders, right? And those who are working for the country, right? And even not they are getting praised, or in another sense they are not getting in the limelight, right? Can I say our black commandos? The special category of a persons, right? The special category of the personals, right? Apart from those who are working on the international borders, who are protecting us on the international borders, right? Garuds, new unit, right? So you can understand the actual difference between us and the peoples, those who are working into the surrounding to protect us, right? At the regional level and working at the international borders, working, right, working with the confidential matters of the country, right, for the securities of the country. Okay, so this kind of the difference is there into the spatial category. And actually, right, we have studied ourselves. We are the common categories of the motion. The person who are protecting us at the regional and state, they are a very different category. The spatial category, and those who are working at the international border, again they are coming into the different categories, right? So there are some categories of the motion, and among that the periodic motion is in the spatial category. Let's see how. We have seen, right, number of motions till now. We have seen UAM. It stands for uniformly accelerated motion. We have seen curvilinear motion, right? So in another sense, it is the case of the non-uniform motion. We have seen the case of the projectile motion or the motion in 2D. Lots of things are there, right? We have seen the calculus method. We have seen the formulas related to it. We have seen the cases of the projectile motion. We have seen the cases of the circular motion. Thousands of types of motions we have seen. But how periodic motion differs from them? Right? How periodic motion differs from them? Right? So if we want to define that stuff, then simply we can define it. Motion that repeats at regular time intervals. Right? Motion that repeats at regular time interval. Thousands of definition you will get into the, right? Okay, ample of resources are available into the market, and among them the thousands of definitions are there. Some might be controversial, some might be not, but here, right, as usual, I used to say in all of my lectures, whatever I'm representing in front of you all, right, it is all which is quite easily understood by our audience, right? So the things that are represented well in front are easy to understand, right? Considering the same psychology, I've kept the definition of the periodic motion in front of you all. Motion that repeats at the regular intervals of the time. Sir, which kind of the motion that is repeating at the regular interval of time? Every day I am getting scolded by my mother. Is it a periodic motion, sir? At the regular intervals of time, कोई मेरा काट के चला जाता है, right? Breakup happens, sir. Is it a periodic motion? In every test, right? Okay, the graph of my marks is getting decreased. It is because of you, sir. Physics, in physics also it is because of. So is it a case of the things are getting repeated? Every time I am getting less marks in an examination, sir. Is it the case of the periodic motion? Right. Every time when I'm sitting ideally in my room and having chit chat with my mobile phone and suddenly mom appears, need to buy things from the supermarket. Will you move on? Will you move for that? Question mark. Every time it happens. Is it a periodic motion? Sir, you told us, na? Motion that repeats at the regular interval of the time. Sir, these are the things, right? Okay, that are continuously happening in our lives, sir. These are the common man's problems. So is it, sir? Is it the periodic motion? Question mark. Right? Is it the periodic motion? I must say no. Periodic motion has no relation with what path it is taking. Periodic motion has no relation with any parameters. It has only relation with one, that is time. Right? So, example. Right? Example. Okay. Motion of a satellite. I'm not fixing up the things in the name of the satellite as a geostationary satellite. Right? Let's generalize these things. Whether it is a geostationary satellite or whether it is any weather forecasting satellite, any kind. Right? They are repeating the same path, whatever path or whatever, see, on whatever path they are orbiting around the earth. We are not interested, but the same path they are going to continue for the infinite amount of the time. Suppose one, let us take an example, right? One satellite is launched near the pole, right? And it is, see, suppose this is an earth. Suppose one satellite is launching and it is following this path. For infinite amount of the time, right? This path is being followed by the satellite. And even, right, the time period of the completion of one revolution is also same every time. Right? Time period of completion of one round. Suppose geostationary satellite is taking 24 hours, right, to complete the one round. Example. Suppose any X satellite is taking, right, 48 hours to complete the one revolution, right, revolution around the earth. Right? So whenever it is moving on for the second time, right, for second time it is also taking 48 hours. For third time it is also taking 48 hours. For fourth time it is taking 48 hours. For fifth time it is taking 48 hours. For infinite number of the time intervals. In another sense, right, okay, for each path, for each round, each revolution, the time is same. That's why I define as motion that repeats at the regular time intervals. Right? We have, why it is a special category of the motion? We have bounded time. Suppose these are the two rigid balls. In between two rigid balls, right? Okay, a ball is getting continuous, like, right? Ball is elastically colliding with each wall. Right? So suppose let us take an example from t is equal to 0. It is starting here. It is getting collided 1 second, 2 second, 3 second, 4 second, 5 second, 6 seconds. So on the every 1 second, right, the path is getting repeated. It is going like this way, it is this. So every 2 seconds, extremely sorry. 1 second moving forward, 1 second moving back. Path is complete. Again 1 second moving forward, again 1 second moving back to its original position. Again 1 second. Now suppose if we are changing the path like this way. Suppose from t is equal to 0, it is getting started. 1, 2, 3, 4. On the time interval of the 4 seconds, right, one path is getting repeated. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. That is the periodic motion. The best example of the periodic motion, PT exercise. Right? 1, 2, 3, 4. Periodic motion. The same path. Suppose 1 second, 2 second, 3 second, 4 second. The same path you are going to repeat in next 4 seconds. 1 second, 2 second, 3 second, 4 second. Again, 1 second, 2 second, 3 second, 4 second. In all of so examples, right, paths are different, but one thing is fixed, that is time to complete one entire revolution, time to complete the entire path. That is the periodic motion. So this is one of the example. Now let's move on to the another example to understand, right, why I have said now why it is a special category of the motion. Another example, right, okay, it is roller coaster ride. Right. This is a path of a roller coaster. Let us take an example, right? Roller coaster is moving on from point A, right, to point B. While moving on from point A to point B, right, the total time taken by the roller coaster in the first round. In first round, while moving on from A to B, the total time taken by the roller coaster is 6 seconds. While in second round of the roller coaster, when it is moving on from A to B, yes, obviously it is taking 6 seconds. While moving on from the third round, from A to B, again it is taking 6 seconds. Path is not fixed, right? But that same path, whatever the path you want to take, we are not interested. Whatever the time you want to take, we are not interested. But that path should be repeated, right? And time taken by an object to complete that entire path, on every interval it should be same. On every interval it should be same. If we're talking about the roller coaster ride, the first round of the roller coaster ride between 2 is 2 point. Second round, 6 seconds. Third round, 6 seconds. Fourth round, 6 seconds. Fifth round, 6 seconds. Thousandth round, 6 seconds. So every 6 seconds between A and P, this path is repeated. This is just to understand. The entire path of the roller coaster is not only between A to B. The entire path is something else. Okay, if you want to talk about an entire journey of a roller coaster, right? So from a desk, you are starting, the motion of the coaster is getting started, right? Okay, you are completing the entire journey and coming back to the same point. The path is quite uneven. Within the time span of 35 seconds, the roller coaster is covering the one round. Again, if it will move on for the second round, it will take 35 seconds. Again, if it will move on for the third round, it will take 35 seconds. Again, it will move on for the fourth round, it will take 35 seconds. Right? So, path in the entire, right, and an entire, like all of those theme parks, right, the path of the roller coasters are not same. But, right, whatever the amount of they are taking, the time they are taking for completion of the one round, the same time they are taking for the second round. So that's the periodic motion. We are not interested into the path, right? Into the fixed time interval, the path should be repeated, right? Into the fixed time interval, right, the path should be repeated. So it means that that's why it is a special category, right? On the regular time intervals, the path is getting repeated, and that's why, right, it is the function of time. The periodic motion is function, right, of time. The person, those who are protecting us at the state level, the regional level. Right? It is a function of time. Right. Again, if I want to justify this thing, x is equal to t plus capital T. At any time t, if you want to find the position of a particle, this is time period for one revolution. Right? The periodic motion is a function of time. Oscillatory motion. Now let's move on into the deeper of the topic, right? We are having one special characteristics of the human, right? In Hindi they are known as, in English they are known as rigid. Those who are rigid in their nature, right? They never used to accept the suggestions from anyone. They always used to consider their own experience as the master, right? And they always used to move on according to it, right? If someone suggests them, if someone gave them advices, they always used to say, yes, very good. But internally, they never used to consider them. They never used to accept advices. They are not having the capability to accept the advices, right? Those characteristics, see, entire human race is there. Among them, we are having some special characteristics of the humans. They are known as rigid. Rigid, the person with a rigid character. The person with that rigid psychology, if one time things will get worse, always he used to think the things are going to get worse, sometimes worsen, right? So the spatial category. We have seen curvilinear, we have seen motion in 2D, projectile, circular, motion in vertical circle, lots of things we have seen. Motion in 1D, but okay, in none of the case we have seen, right, the path is getting repeated into the specific time interval. No. If particle is getting projected from one point, it is following this path. Obviously, this path is not getting repeated. No. And if suppose in any case, if we have seen the path is getting repeated, then I am damn sure that we haven't saw, right, that case in which the time interval is fixed. Right? The time interval is fixed. Okay, oscillatory motion, how it is different from the periodic motion, right? And how to, right, just simply define into the very short. Periodic motion is a spatial category of the motion. They are rigid. Why they are rigid? I want to follow only one path, and that also at the regular time intervals. Rigidness. But in that case, that is one positive. It is different from others motion, as I said, 1D and everything. But in that case, we are having one simple thing. What? Right. In that case, we are having one difference. What? Right. You are in a periodic motion, you are having a freedom to select the path. You are having a freedom, right, that in what amount of the time you want to complete a path. My rigidness is what? You have to complete the same path, right, at the regular. You have to repeat that path at the regular time intervals. That freedom of selecting a path get vanish into the oscillatory motion. Oscillatory motion, we are, right, with the foundations. One, the human race. Among them, people with the characteristics rigid. They are rigid, the rigidness. But with one freedom is periodic motion. But now the freedom is getting vanished. They are rigid, but they are more rigid as compared to the previous one. I will only follow to and fro. That is an oscillatory motion. Right? To, fro, to, fro, to, fro. Right? In the case of the periodic motion, one rigidness states that. Right? In the case of the periodic motion, one rigidness states that. Right? Okay? It was the freedom was given, right? You can select your own path, but it should get repeated at the regular time intervals. But in oscillatory motion, even we are not, right, given the freedom to select a path. We are having only one, to, fro, to, fro, to, fro. Either it can move on from the left side, either it can move on from the right front back, or either it can move on to the up down. So generalized form of this, to, fro, to, fro, to, fro. Oscillatory motion, right? Oscillatory motion, to and fro of a particle at regular time intervals or fixed time intervals, right? To and fro of the particle, right, at the regular time intervals, right? This is defined as, right, this is defined as the oscillatory motion. You can see in this visualization, right, to, fro, you can see, right? Now to, fro, with respect to what? With respect to one point. In first case, I am rigid, but you can select your own path. In the case of the periodic motion, I am rigid, but you can select your own path. In the case of this, right, I am rigid, but you have to select whatever path I am giving you. Right? Yes or no? You have to move on, right? Okay, you have to follow the path of to, fro. Oscillatory motion. SHM. Okay, let's completely demolish the freedom, but okay, we are going to see that stuff, right? It's okay. Like the periodic motion, it is a function of the time. Oscillatory motion, right? Why? I must say why. Why particle is only performing this kind of, yes, you said it is a special category of the motion, right? We accepted it. You are sir, right? We accepted it, right? Because you have delivered, right? We trust you, we accept it. But why? Which thing, right? Okay, which thing, right, bounds the object? Which thing, which factor, right, is bounding in the object so that it is moving, right? It's following this path, to, fro. We are going to see this stuff, right, into the SHM, but generally, right, all the oscillatory motions are represented by this equation. F is equal to minus kx to the power n. All where n varies from 1, 3, 5, right, up to value of the n. All the oscillatory motion. Now here lies the reason, right? In this equation, right, okay, there lies the reason why particle is performing to and fro. You can see now, this is a reference point, right? With respect to this reference point, when particle is moving to, fro, right? As I said in the previous case, right? As I said into the previous case, periodic motion, right, it is a spatial category, right? So that's why the equation of the periodic motion completely depends on time. We have seen na, it is the function of time, right? It is the function of the time. Similarly, why, right? If it is following to and fro, it's okay, you can, right? Okay, we are not, see, it is like that na. If someone is getting more rigid, then obviously it gets differentiated from the else crowd, right? It gets differentiated from the crowd. So the same thing, if you want to follow to, fro, okay, it's okay. But what is an equation, right? Okay. Now, what is an actual difference between the periodic motion and oscillatory motion, right? So I'm going to write down one note here. All oscillatory motions are periodic, but all periodic motion are not oscillatory. All the oscillatory motions are periodic because in all of those oscillatory motion, right, there is only difference of displacement, right? And the thing common in all is they are going to follow to fro path, to fro, right? So that's why all of those oscillatory motion are the part of the periodic motion, but all periodic motions are not oscillatory. Why? because in periodic motion still we are independent to select the path. In both of the cases, right, okay, at the regular time intervals the path should be repeated, but in periodic motion you are having a right to select the path. In oscillatory motion we are bounded, compulsory we have to follow to fro. Compulsory we have to follow to fro. So this is the most important note, captain. For all the oscillatory motions are the periodic, but all the periodic motions are not oscillatory. Now let's move on to the most important part, the fundamentals of the SHM. And before that, right, I want to clarify the one simple term, right? As I told you all, the equations of the oscillatory motions, the all oscillatory motions are represented by this thing. When the value of n is getting 1, we are getting this equation f is equal to minus kx, where, right, f is equal to minus kx, okay, where f is the restoring force. F is the restoring force of the particle, right? This one is an SHM. Now here, right, okay, the students might be having the another question into the mind. Sir, we are easily able to understand the difference between the periodic motion and an oscillatory motion. We are easily able to understand the difference between the periodic motion and an oscillatory motion, but still we are getting confused between oscillatory and the SHM. Right? Still we are getting confused between the oscillatory and SHM. So let's see that stuff. Right? F is equal to minus kx to the power n. F is equal to minus kx to the power n. If n is 1, then it is SHM. Suppose value of the n is getting changed. Suppose n is equal to 3, then we are having the equation of f is equal to minus kx cube. Right? Okay. In another sense, right, non-technically, if you want to compare the SHM and oscillatory, then I must say SHM is a micro version of oscillatory motion. In oscillatory motion, we are having the high displacement. In SHM, that is the difference. SHM is also bounded, right, by one fact. Okay, SHM is also bounded by one fact. What? Compulsory it is to perform to and fro with respect to one point. Right? Compulsory, right, it has to perform to and fro with respect to one point. To, fro, with respect to one point. To, fro, with respect to one point. But, question mark. To, fro, with respect to one point. But, displacement of SHM, displacement of a particle that is performing SHM, it is quite less as compared to the particle that is performing the oscillatory motion. In oscillatory motion, ding, ding, jula. In SHM, you can see, you can compare this displacement, it is quite less as compared to jula, like this. In both of the cases, reference point is fixed. With respect to the reference point, with respect to that mean position, the particle is performing the oscillation. Right? Okay. As I said, this thing is responsible. This equation is responsible, and that will give you the reason, right, that why to and fro. Why? This equation is going to give the reason. Right. First of all, let's analyze, right, okay, the concept of SHM. As I said, non-technically, the SHM is the micro version, right, of oscillatory motion, and given you the examples also. Now you can see in this visualization, right, okay, with respect to This is my reference point, right? This is my reference point. Now with respect to the reference point, with respect to this reference point, particle is getting 2, particle is getting fro, again it is getting 2, it is getting fro, it is getting 2, right? So this reference point is fixed, right? Okay, now most important thing, displacement in SHM of an particle displacement is SHM is less, right? It is smallest compared to the particle, right? Displacement of a particle, those who are performing the oscillatory motion, right? So SHM, it means to and fro, right? But with small displacements, right? With a very small amount of the displacement. Mobile vibration, right, is an SHM. And mobile vibrates. Now I'm giving you all an example in front. Suppose if it is just kept randomly at a desk, right, and someone suppose calls you, right? Okay, and if it is in a vibration mode, then it is going like, right? So that vibration is SHM. Right, that vibration is SHM, right? Vibration is SHM. But if I'm talking about a pendulum, right, that is attached into the wall clock, right? Have you seen that antique wall clocks, right, into the films, into the horror films, right? Okay, when right, in the horror films you heard about na, at 12 heroine suddenly heard the voices. कोई मुझे पुकार रहा है. Why? मुझे जाना होगा. कौन पुकार रहा है? Why you want to clear that mess? Why you want to reveal, right, who is calling you at 12? And suddenly that antique wall clock that is present into that palaces, that horror palaces, gives the confirmation, right? At 12, right, suddenly at 12 it sounds tung. Now suddenly heroine was thinking about someone who's calling in, when it tung, kaun hai, right? That pendulum that is hanging in the antique wall clock. So displacement of it is quite, so that is an oscillatory, and the mobile vibration is an SHM. Right? कौन है? क्यों है? And suddenly when she moves on, and we are having that background, like this we are having the background music, right? Horror, the most common, right, the stereotypes of the Indian horror cinema, right? The stereotypes, right? Okay, one day, right, we are going to upload one stand-up, right? That stand-up will be completely based on an academics part only, right, on the student life only, but definitely one day we are going to upload that stand-up, right? Okay, so SHM, to and fro, but with a very small displacement. Again, we are moving about to our statement Y. Okay, F is equal to minus Kx, right? This thing is responsible for to and fro of the particle, right? And this is named as the restoring force. But how and why? Right? For that, let's understand one example. What happened? I think as of the cause of the SHM. See, let us take a very simple point. You can see into the visualization also, right? The reference point with respect to which the particle is moving to and fro, it is known as the mean position of the particle. the most important note, right, I'm writing regarding the mean position is mean position is never fixed. As I can understand in previous, right, presentation slide I wrote it is a fixed, but never fixed, it means that what the statement means, for one kind of the motion, if the mean position is at this point, right, for another kind of the motion, right, it may differ. It is not fixed that this thing is going to be, right. One thing about the mean position is going to be fixed, that is t is equal to 0. Only this thing is fixed. Only this parameter of the motion is fixed, right? You can consider t is equal to 0. Yes, mean position. Now it can be anything, right? With respect to any point, it can perform to fro, right? With respect to one relative, right? Okay. On the occasions, you can perform to fro, right? Okay. So this is a mean position with respect to which the particle is performing. Now, suppose let us take an example, right? If spring is attached to it, a very simple example, right? Suppose it is gently stretched and released. Suppose it is gently stretched and released. It is gently stretched and released. Now what will happen? Suppose if it is just gently stretched, right? Obviously it is going to shift itself from the mean position, right? Okay, and the spring is going to get elongate. Initially the spring was in its natural length, right? Spring was in its natural length, but suddenly as it is gently stretched and released, right, obviously, right, it will get elongated. Now when it is gently stretched, obviously we are having an extension in it, and as because of that, one restoring force is developed. Why? Because the spring is elastic in nature. This is one of the best examples, right, to understand the concept of the why springs are taken in an SHM, because this is the best example to understand this stuff, right? As because, right, of restoring force F, that is equal to minus kx, right, particle crosses its mean position second time. It was gently stretched by delta x. Obviously, if spring is getting elongated, right, as because of this restoring force, right, some amount of the potential energy is getting stored. As of that potential energy, when it is released, entire potential energy is going to convert into the kinetic energy. And obviously, one thing is fixed, the surfaces are smooth. So when it is gently stretched, we are having the maximum potential energy. Slowly when it is released, entire thing is going to convert, right? When it is going to come at the mean position, the entire thing is going to convert into the kinetic energy. Now at the mean position, the particle is having the kinetic energy, the maximum kinetic energy. Is it means it is going to stop? No. Again it is going to move into the opposite direction and the spring will get compressed. Sorry. First it was gently stretched, maximum potential energy. Now it is released, entire potential energy, right, while moving from the max position to the mean position, right, the entire potential energy is going to convert into the kinetic. Now at mean position we are having the maximum amount of the kinetic energy. So the particle with the maximum kinetic energy, is it going to stop? No. Then it will move into the opposite direction. Again it will move on to the maximum point. The entire kinetic energy is going to convert into the potential. Like this way, the same path repeats with no energy loss. Actually energy loss is there, damping is there into the day-to-day life. Damping is always there, damping force is always there, right, into the day-to-day life. But generally, right, to understand these things, right, from the theoretic point of view, right, we are not taking any kind of energy losses, right? So as because of this presence of this restoring force, the particle is repeating one path, right, with respect to the common point, and that's why it is SHM. It's performing the SHM, right? That's why it is performing the SHM. So you can see in this visualization, right? Okay, and one thing about this, right? One thing about this is this F is equal to Kx always X with respect to center. It always acts with respect to the center, right? It always acts with respect to the center. Okay, so this is a cause of the SHM. Now let's move on to some of the important parameters of it. Right, you understood now, right? Some of the important parameters, then we are going to see the, right, how, see with energies, how the, right, accelerations and velocities are getting changed, right? First of all, kindly give me amount of a time to drink water, please. Right, oh man. Boom. Parameters, right? This is an actual example, right? If you want to consider, right? So let's take another thing too. Now we are going to analyze the motion of the particle, right? First of all, I want to write mean position. Right, the reference point with respect to which particles perform SHM. Right, this is a reference point with respect to which the particle, obviously this reference point is going to start at t is equal to 0, right, with respect to which first the particle will move on to this point and again it will move on to this point, right? Okay, like this way, to fro, to fro, to fro, right? So first is the mean position. Let's move on to the second definition, that is amplitude, right? The maximum displacement of the particle on either sides. Maximum displacement of the particles on the either side, right, with respect to, okay, maximum displacement, you can see that, okay, just hold on. This is an amplitude. With respect to, this is a mean position, right? Now with respect to this mean position, maximum the particle can go up to this much distance, right? Maximum the particle can go up to this much distance, 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 right? Okay. Right. Time taken by particle for one revolution, or in another sense one oscillation, right, or one round, okay. Okay, just hold on. Like this. Okay, so these are the most important terms. Now let's move on to the how acceleration and, right, velocity as given, because we need to define that equation now. right? We have seen the equation responsible for the SHM, but how acceleration is getting changed, how the motion parameters are getting changed, we need to understand that. And for that, in SHM, we need to understand the variations of the acceleration and velocity in that, right? Okay, suppose this is a mean position, right, with respect to which t is equal to 0, right? This is our reference point and the mean position, right, with respect to which the particle is getting, right, performing the SHM. Now at this position, velocity of the particle is getting maximum and acceleration is 0. Suppose it is given by a velocity in this direction by an external source. Gently velocity is given, right? Okay, why it is gently? Because displacements are not quite large. That's why I said, right, the SHM is a micro version of the oscillatory motion, right? Okay, SHM is the micro version of the oscillatory motion. So here the velocity is getting max. Now suppose this is attached to the spring, slowly, right, it is moving on to this part, this part, this part, this part, and finally reaching to this part. This is its max displacement, right? This is its max displacement. Now see what happened. At max displacement, the acceleration of the particle is getting, see, whenever it is moving from the mean position to the max displacement, now at the max displacement point, for the very fraction of a second, right, it gets stopped, it gets stuck. So at that point, the velocity of the particle is 0 and the acceleration of the particle is maximum. So here you can understand, see, here velocity is maximum, acceleration is 0. Why? Because why acceleration is 0? Because f is equal to minus kx, right? Net acceleration, that is equal to minus kx by m, right? We are having, right, suppose this is attached to the spring, right? We are having any kind of the elongations, x value is 0. Why? The spring is in its natural length. That's why at this position the acceleration is 0. Now slowly spring is getting elongated, right? The acceleration value is increasing. Slowly it is increasing. Slowly acceleration value is getting increased. But acceleration value is getting increased. Why? Because elongation is getting increased. It means some amount of the elongation is there, and slowly work is done. And slowly the energy is stored into the form of potential energy. So at this point, suppose in between these two, here we are having the maximum acceleration and that is also acting towards the center. So at that point, velocity is getting continuously decreased. Right? The velocity is getting continuously decreased. You can understand the difference. And finally, V is 0. Acceleration is getting continuously increased. Velocity is getting continuously decreased. See, nothing is constant. Right? Is acceleration constant? No. Why? Is the value of, see, x in an elongation into the spring, is the value of the x is getting increased? Yes, it is getting increased. Is it fixed? No. Suppose if the value of the x is fixed, then obviously the acceleration is going to be fixed. It's not a big deal. Right? Acceleration is going to fix. It's not a big deal. But here the value of the acceleration is getting continuously changed. Slowly it started from the mean position. Velocity was maximum. Slowly the velocity is getting decreased. The acceleration is getting increased. Why? The value of the elongation into the spring is getting increased, and as because of this, right, the value of the net acceleration is getting increased. Now, when it is at the mean position, right, this is the first round. The variation of the acceleration, right, while it is moving on from x is equal to 0, right, to x is equal to positive a. Now, let's move back and let's come back to the mean position. Now we are moving from x is equal to positive a, right, to x is equal to 0. Now what will happen? At this point, potential energy is maximum. Acceleration, see, velocity of the particle is 0, but acceleration is maximum and also acting towards the center. So it will force this particle to come back to its original position, and that is mean position. So what will happen here? The acceleration is maximum, 4 arrows. Velocity is 0. Slowly acceleration is going to decrease. 3 arrows, velocity 1 arrow. Acceleration 2 arrows, velocity 2 arrows. Right? Acceleration 1 arrow, velocity 3 arrows. Right? At this point again acceleration is 0 and velocity will become maximum. So upper part is while moving from x is equal to 0 to x is equal to positive a. Lower part while moving on from x is equal to positive a to x is equal to 0. Now while reaching to this mean position again, we are having the max velocity, but while completing half of the oscillation, right, the direction of the velocity is reversed. We are having the max amount of the velocity, but in the previous case it was acting towards right, but after completing the half part of the revolution it is acting towards left. It is acting towards left. So again here velocity is maximum. Now let's move on from x is equal to 0, right, to x is equal to negative a. X is equal to 0 to x is equal to negative a, right? Okay, see, velocity here it is maximum, 4 dots, right? Acceleration, right, only 1 dot. 1 arrow. Slowly. Now it is going to move on from like this way. This will be the x is equal to negative a point. Right? Now here, velocity, here we are having 4 dots, here we are having 3 dots. 3 arrows, here acceleration 2 arrows. Velocity 2 arrows, right, acceleration 3 arrows. Now slowly the acceleration is going to, now velocity only 1 arrow, acceleration 4 arrows, right? Okay, like this way it makes my velocity will be 0, right, and acceleration will be maximum, and that is also acting towards the center. Now particle has reached to the max position. Now we are moving on back from x is equal to negative a, right? X is equal to mean position, that is 0, right? X is equal to mean position and that is 0. Obviously what will happen, right? Here the acceleration 4 arrows, velocity is 0, right? Acceleration 3 arrows, right? Velocity with 1 arrow, acceleration with the 2 arrows, velocity with the 2 arrows, acceleration with the 1 arrow, velocity with the 3 arrows, right? And again we are going to back at the same position. Now while moving, after completing the entire oscillation, the velocity, direction of the velocity will get changed. Again it will move back to the positive a side, again it will come back, again it will move on to the negative side, again it will come back, again it will move on to the positive side, again it will come back, again it will move on to the, like this way, right? To fro with respect to the mean position. And this is how, see, here by this explanation you are aware the acceleration and the velocity are getting changed. Yes, the acceleration and velocity are getting changed, I can understand, but is this change uniform? One question I want to ask you in front of you all, right? Change in velocity is uniform? I must say no. Why? If the change of the velocity is uniform, then always acceleration of the particle is constant. But in the case of the SHM, the acceleration is also getting varied. Right? So, change in acceleration and velocity, both is not uniform. Only one thing is uniform about it. What? At the regular time interval, velocity is 0, acceleration maximum. At the regular time interval, acceleration maximum, velocity 0, acceleration 0, velocity maximum. At the regular time interval, you can see this, right? Okay, at the regular time interval, right? See, at t is equal to 0, right? Okay, velocity maximum, acceleration 0. At t is equal to capital T by 4, right? Velocity is 0, acceleration maximum. Again at capital T by in another sense T1 and T2, right? Again at the time T2, right? Okay, what is happening? Velocity maximum, acceleration 0. Again at time T3, velocity 0, acceleration maximum, right? So at the mean and max points, right, the values of the accelerations are fixed, but it in between this two, the variations, right, are measured, right? Variations are measured, right? Okay, so it means that if I want to represent the SHM, I need that equation in which at regular intervals of, see, let us take a very simple example. How to represent the equation of the SHM, right? Only the equation of the restoring force is not an equation of SHM. Suppose this is the mean position, right? Okay, this is the mean position, x is equal to 0, right? At the regular interval of the time, it is reaching to x is equal to positive a, right? X is equal to negative a. So at the regular intervals, the position of the particle is getting changed, 0 to a to minus 0, 0 to minus a to 0, 0. It means I need to, if you want to represent this SHM, you need that function whose value is getting repeated at the regular intervals of time. Velocity, here it is maximum, acceleration is 0. Here acceleration is maximum, velocity is 0. Again here acceleration is maximum and acting towards the center, velocity is 0. Right? Now, to represent motion parameters, we need a term that continuously repeats at regular time intervals. That's why we are defining SHM, the equation of SHM, x is equal to a cos of omega t plus phi, right? Or x, suppose if it is performing into the y direction, then we are saying y is equal to a this is an equation of SHM. Right? Conditions to check, right? There are some specific conditions that will determine whether the particle is performing, right? Questions based on this are also asked in examinations, right? But it's okay. Why? See, value of the cos is getting changed between 0 to plus 1, plus 1 to minus 1, right? The minimum value of the cos is 0. Right, and the opposite either sides, the maximum value is plus 1 and minus 1, right? Sine value changes in between 0 to positive 1, right, and in between negative 1, right? This is not only the reason that SHM is represented by this equation. Behind this, there is a long derivation also, right? And apart from this, right, the entire Phasor method is based on it, right? Entire Phasor method is based on it. This is not only the reason, right? Okay, behind this there are there is much more thing to discuss. A lot of long derivation is there, but we are not interested in that part right now. Okay, and the entire Phasor method is also based on it, right? But the one thing is common, the value of the cos is getting continuously repeated. So as because of that, right, the value of the this will be the max displacement, that is known as amplitude. The value is getting cos as 0, the entire thing as 0, right? It means what is happening, the value of the x will be 0. So that will be the mean position, right? If the value of the cos is getting completely 1, x is plus a, then it is at the max displacement. Value of the cos entire is going to have the minus 1, then we are having x is equal to minus a. Right? So this is how the position variation. Now let's differentiate this equation right, with respect to time. Let's differentiate x, right, with respect to time. We get the velocity variations. V is equal to dx by dt. So that is equivalent to what? A of omega, right, negative sine of omega t plus phi. What is omega t plus phi and everything? We are going to discuss that in detail. And so these are the velocity variations. Suppose again I am differentiating, right, v with respect to time. We are having the acceleration variation. A is equal to negative of a omega square, right, okay, cos of omega t plus phi. In another sense, right, this part and this part, I want to discuss that thing in detail. Maximum velocity of the particle is a omega in terms of magnitude. Maximum acceleration of the particle is minus a omega square. If you want to write this equation, it is minus omega square x. This is a condition to check, right? This is a condition, right? Don't get worried, we are going to discuss this thing in detail. Right, here we are getting the new things. This is the maximum velocity, or in another sense it is also known as velocity amplitude, right? It is also known as velocity amplitude. In another sense it is known as acceleration amplitude. At this point, plus a is amplitude, right? A omega is the velocity amplitude, minus a omega square is an acceleration amplitude. Why this minus? This minus sign indicates it always, right, x towards the centers and opposes the move. It always x towards the center, right? So what is a condition? If particle satisfies the condition or the equation A is equal to minus omega square x, right, then we can say the particle is performing the SHM, right? We can say the particle is performing the SHM. So these are the equations. Now we are going to discuss these equations in detail and the respective parameters. X is equal to A. Let's take the easy thing to understand. Y is equal to A sine of omega t plus phi, right? Omega t plus phi. What is Y? Position of particle at any time t. How the variation of the position of the particles are measured? What is A? Amplitude, right? Now see, what is this, right? This is known as phase. The value of the phase is getting changed. As because of this, right, the value of the sign is getting changed. And as because of this, the position of the particle is getting changed. Similarly, in velocity equation, velocity of the phase is getting changed. Among them, the velocity of the particle is getting changed, right? Similarly, in the equation of the acceleration, the velocity of the phase, the value of the phase is getting changed, and with respect to it, everything is. This phase, this is known as phase. What? Omega t plus phi. Phi is the initial phase, or it is also known as epoch, right? This will decide mean position, right? This will decide the mean position of the particle, right? The initial phase and epoch, this will decide the mean position, right, from which the particle is going to start. In another sense, can I say t is equal to 0 is going to, right, define the initial phase of the epoch. Second, omega 2 pi by capital T. This is known as angular frequency, right, of a particle that is performing an SHM, where T time period of one oscillation or round. Okay, so if I want to represent this thing, how I can represent? See, y is equal to a sine of 2 pi by capital T into small t plus phi. Initial phase at t is equal to 0, that will show from which position the particle is starting its motion. Angular frequency with respect to this time period, at what time you want the position of the particle. So this capital T is time period, the small t is at what time you want the position of the particle. At what time t the y is known, right? So this is also an explanation about it, right? Similarly, the same thing happens for the velocity, right? And obviously there are some graphs related to it, right? There are some graphs related to it. And before moving on for the graphs, let's understand the one of the examples. First, if at t is equal to 0, particle is at x is equal to 0, what is initial phase? This thing is needed. Y is equal to a sine of omega t plus pi, right? At t is equal to 0, x is equal to 0. In another sense, let's take an example, y is also 0, right? Okay, y is also 0. So it means 0 is equal to a sine of omega t plus pi. We are getting the initial phase as 0, right? We are having the initial phase as 0. Second, if at t is equal to 0, y is equal to positive a, what is an initial phase of the particle? Obviously, what is an equation of SHM? Y is equal to a sine of omega t plus pi, right? This is in best example how the mean position is getting changed. Plus a, right, is equal to a sine of, right, omega t plus phi. From this point the particle is starting its position. 1 is equal to sine of omega t 0 plus pi. So sine phi, that is equal to 1, phi is equal to, the initial phase is pi by 2. This thing is going to, right, help in understanding the concept of the phasor, right? Now third case, suppose if x is equal to plus a by 2 at, or y is equal to, y plus a by 2 at t is equal to 0, then what is an initial phase? Obviously y is equal to a sine of omega t plus pi, right? So in this case what will happen? Plus a by 2, that is equal to a sine of 0 plus phi, sine of phi, that is equal to half, phi, that is equal to pi by 6. This is an initial phase of the particle. From this point, right, the particle starts performing the SHM, right? This is how the things are getting changed. Conditions to check whether the particle is performing the SHM or not. Suppose any random equation is given in the question. Suppose they said us that y is equal to a sine of omega t, right? They said us, suppose a particle is performing some random motion and the equation of the motion is represented by this. Check whether it is performing the SHM or not. check whether it performs. Simple, it's very simple. Differentiate this equation, right? So velocity is equal to a of omega cos of omega t. Again differentiate this equation with respect to time, right? Differentiate with equation with respect to time. We are getting acceleration is equal to minus omega square x. If this condition is satisfied, the particle performs as such. Right? So like this way. Now graphs of SHM. X is equal to A cos of, or in another sense, suppose if you want to represent the first graph, that is displacement versus time graph. Lots of graph we are going to see, right? Y is equal to A sine of omega t plus phi, right? So this is the time, this is the displacement, right? Right, this is a displacement versus time graph. Second, velocity versus time graph, right? Velocity versus time graph, right? V is equal to A of omega, right, cos of omega t plus phi, right? Okay, in another, let's move on. Phi, we can remove this phi, right? We can remove this phi. Okay, now velocity versus time graph. What will happen here? This is the variations of velocity, right? Okay, third equation, the acceleration versus time graph, right? What is an equation? A is equal to negative of omega square x, right? Okay, and that is equal to sine of omega t plus phi, right? Like this way we are going to have the acceleration versus time graph, right? So these are the three basic graphs. Now let's move on to the fourth one, right? Velocity versus displacement graph, right? Velocity versus displacement graph. We saw V is equal to A of omega, right? And that is cos of, right, omega t. Okay, suppose if you want to replace this term, V is equal to A of omega, we can replace this as under root of 1 minus sine square omega t. By replacing this, we are having V is equal to, right, omega under root of a square minus x square. This is the equation of velocity with respect to displacement, right? This is the equation of the velocity with respect to the displacement, right? Now for this, right, the graph would be ellipse. Why? Suppose it is v square omega square, it is a square minus x square, right? So it is v square, it is a square omega square, right, minus omega square x square, right? So it is v square plus omega square x square is equal to a square omega square, right? And simply if you want to represent this term, okay, so this shows the graph of ellipse, right? This is x square by a square plus y square by, right? See, this is a graph I'm showing you. Right, okay, this is velocity and this is a displacement. Okay, so here it will be v square by a square omega square plus x square by a square is equal to constant. This is the equation of ellipse. Right, this is the equation of ellipse. At this point we are having the maximum value of a omega, that is max velocity, and here we are having the maximum value of positive a. At this point we are having the negative a, and this point, right, we are having the negative a of a omega. Okay, negative a omega means direction is getting changed, magnitude is constant, right? So velocity versus displacement graph, right, it is what? The ellipse, right? Velocity versus displacement. So you can see this in the equation, that is v square by a square omega square plus x square by a square, that is equal to constant. Can I compare this to equation? X square by a square plus y square by b square is equal to constant, right? A and b are semi-major axis and semi-minor axis, right? So this is the value of the a and this is the value of the b. A is the semi-minor axis and b is a semi-major axis. I'm sorry. Right, but that completely depends on the graph, how things are getting here. Value of the a and b gets varied, right? But it depends on the how ellipse is been plotted, right? So this is the velocity versus displacement graph. Now third graph, that is the fifth graph, that is acceleration versus displacement, right? Acceleration versus displacement. Okay, acceleration versus displacement. Now let's see this graph. A, that is equal to minus omega square x. Now omega is it's constant, right? Omega is kept constant, so it means that a is directly proportional to x. If a is directly proportional to x, obviously y is directly proportional to x, right? Removing this proportionality sign, I'm getting y is equal to mx, right? So this will be the equation, right? The graph will be of straight line. Graph will be of straight line, right? Graph will be of straight line. Right? Acceleration versus displacement graph, right? So it will be like this way, but here the slope is negative. Slope is negative. Why? A is equal to 9 minus omega square x. In that case, slope is negative, so graph is like this way, right? Acceleration versus x. I'm sorry. Yes, graph is like this way, right? This shows the theta is obtuse, right? And slope is negative. Similarly, if you want to calculate the force versus x graph, right, then we are having the same another, right? F versus x, right? Similarly, we can write it down as, okay, we can write it down as right, F, right? Or if you want to write it down it as MA, A is equal to minus m omega square x, right? So force is equal to minus m omega square x. So this is also, right, the force versus displacement graph is also same, right? It is following y is equal to negative of mx condition, right? So graph is like this way, right? In this, the slope is minus, the slope is omega square. Here the slope is m omega square. There is only one difference. Okay, so these are the different graphs of the SHM. Now what is an actual difference between the oscillatory motion and the SHM, right? What is an actual difference between the oscillatory motion and the SHM? Now let's understand this thing. right? Come on, everyone. As I said, vibration of the mobile, right? It is an SHM, right? Pendulum, it is the oscillatory motion. Okay. Now, before moving on to the energy, let's understand. Right, we have seen the essay, or we have seen the concepts of the periodic motion. We have seen the concept of the everything we have seen, right? Now we will understand the variations of the energy in SHM, and by one shot, more than 10 to 12 examples we are going to see. Right, first of all, we will move on to the concepts of the energies into the SHM, and by one shot we are going to see the all of the examples, right, for the concepts we have understood till now. Okay, so now let's move on to the energy in SHM. So students, let's move on to the energy variations in SHM. How the energy is getting varied. See, you can see this graph, right? We are going to see the equations also. We are going to see everything we are going to see, right? But here, first of all, in SHM, the most important thing that I want to show you all, that I want to write in front of you all, that no resistive forces are present. Right, no resistive forces are present. Okay, no resistive forces are present. So in this case, what will happen? See, according to the work energy theorem, work done by all forces, that will be change in kinetic energy of the particle, right? Work done by all forces will change the kinetic energy of the particle. Now, what kind of the forces are there? Right, what kind of the forces there is a possibility of what kind of forces it can do the work. Work is done by conservative, work is done by non-conservative, work is done by external, that will change in kinetic energy. Right, so this is the negative delta U plus work done by non-conservative plus work done by external, and that is equal to delta Q. It means here work is done by non-conservative plus work is done by external, that is equal to delta K plus delta U. Right, delta K plus delta U, right? Delta K plus delta U. Okay, so here, work done by non-conservative plus work done by conservative, right? That is equal to delta K plus delta U, right? Delta K plus delta U. Now what will happen? See here, no dissipative forces are there. It means work done by non-conservative force will be 0. Object is gently pushed, so work done by external agent is 0. So here, whatever the variations are going on, right, okay, it is in between the kinetic energy, right, and the potential energy. So in this case, the mechanical energy is conserved, and we are going to deal only with the kinetic energy and the potential energy. Everything is going at the one surface level, so there is no role of the gravitational potential energy. But yes, we are going to deal with the kinetic energy, and as spring is attached, the elastic potential energy is involved, right? Elastic potential energy is involved. So from this, right, one thing is confirmed. Kinetic is getting changed to potential, potential is getting changed to kinetic, kinetic is changing to potential, potential is getting changed to kinetic. But what is an actual equations of it and the graph? See, let's take the same example. This is a particle at t is equal to 0, right? This is the mean position of the particle, or in another sense we can take the, right, a reference point. Right? Okay. Now, at the mean position, the velocity of the particle is maximum. Velocity of the particle maximum, it means that it is having the maximum kinetic energy. Acceleration of the particle is 0. It means that potential energy is 0. Now you will be having one doubt. How the acceleration of the particle is associated with the potential energy? Acceleration equation was minus kx by m. Right? Here x is an elongation or the compression that is measured in the spring. Right? When external force is applied or in any conditions, right? X is an elongation or compression. At the mean position, x is 0. It means elastic potential energy is also 0. Indirectly, I can understand potential energy is not having any relation with. There is a relation, but we are going to discuss that into a different way. But acceleration is related to the compression and elongation, and even the potential energy is related to the compression and elongation. At the max point, at the max displacement x is equal to positive a, can we say that what? The velocity of the particle is 0, it means that kinetic energy is 0. And at this point acceleration is maximum, it means that, right, potential energy is maximum. Actually it is not that much 0. Whatever the variations are going on, right, it is going on between minimum and maximum. Right, nothing is perfectly 0. Right, here the velocity for theoretical purpose it is 0, but practically, right, okay, nothing is 0. Whatever the variations are going on, it is in between the maximum and minimum. Right, whatever the variations are there, it is between maximum and minimum. Suppose if we are moving on to the x is equal to negative a point, right, so at this point also, right, okay, the velocity of the particle is 0, so kinetic energy is 0, okay, and acceleration is maximum. In another sense, the potential energy of the particle is maximum. What are the equations? The simple, see here, the potential energy is associated with spring. First of all, the potential energy is associated, right, with spring. So it means that it is very simple thing. Potential energy, it is equal to half kx square. Right, in another sense, right, if you want to replace the value of x, it is half x, that is a sine of omega t whole square. In another sense, the equation of the potential energy is half k a square sine square omega t, right, sine square omega t. If you are, see, another equation is half ky square. I have replaced the equation of y. Some students might get confused. Sir, you have replaced the equation of x and you are writing here a sine omega t. You should write here a cos omega t. It's okay. SHM happens into the both direction. If it is happening into the x, then it is x cos omega. If it's happening into y, it depends, right? So this is the equation of the the potential energy, right? Okay. It's half k. Okay. Now let's move on to the next equation, that is equation of the kinetic energy. Half mv square, right? The first equation of the kinetic energy is half m. If I'm going to see, there are two equations of the velocities. One, that is v is equal to a omega, right, cos of omega t, and second, that is v is equal to omega under root of a square minus x square. So suppose if I'm replacing that equation, that is, right, omega square a square minus x square. So I'm getting the first equation of kinetic energy, that is equal to half m omega square a square, or in another sense half m omega square, right, a square minus x square. Equation of potential energy half kx square. Equation of kinetic energy half m omega square a square minus x square. This is the first equation. The second equation of the kinetic energy, K, is half m. If I'm replacing the equation of V, that is a omega, and that is cos of omega t plus phi, or cos of omega t. So equation of kinetic energy is half m, right, a square omega square cos square omega t. Right, if I am replacing the value of k here, we are getting the equation of potential energy is half m square omega square, and that is a square sine square omega t. Right, so this is an equation. This is the first equation of potential energy. This is the first equation of kinetic energy. This is the second equation of potential energy. This is the second equation of kinetic energy. Right, here omega square, that is equal to k by m, right, omega square, that is equal to k by m. Okay, so this is what an actual right. Again, if you want to write this thing, okay, again if you want to write this thing, the 4 equations, right? Okay, then we can write it as potential energy, that is equal to half m omega square a square, right, sine square of omega t. Similarly, kinetic energy, that is equal to half m omega square a square, that is cos square omega t. Another equation of the potential energy, that is equal to half kx square, right, and kinetic energy, right, that is equal to half, right, k of omega into x square minus x square, right? Okay, just hold on, I have written the wrong thing. Okay, half mv square, right, so that is equal to half m, it's a square omega square, or that is half m, and that is omega square a square minus x square. Yes, that's a perfect thing. So that will be half k a square minus x square. Yes, that's the perfect thing. Okay, so these are the first of all, we understood the actual variations of the kinetic energy and the potential energy. Right, now you can see there is a, in equation of the kinetic energy and the potential energy, you can understand, see, equation of the kinetic energy states that it is half m omega square a square cos, right, of omega t. What is an equation of potential energy? That is equal to half m omega square a square, and that is equal to sine square omega t. See, kinetic energy and the potential energy is also varying with respect to time, because in this we are also, in this also we are having the cos and the sine function, right? In this also we are having the cos and the sine function. So what will be the graph of it, right? Let's understand this graph, right? This is the mean position, right? This is the mean position, x is equal to 0, right? This is a max displacement, x is equal to positive a, right, and this is in another side, either side x is equal to negative a, right? So if I want to plot this graph, right, if I want to plot this graph, arey yaar, I'm sorry for that, right? X is equal to 0, right? If I want to plot this, right, so at x is equal to 0, right, the velocity is maximum, the kinetic energy is maximum. Graph will be like this way of the kinetic energy, right? At x is equal to 0, velocity is 0, right? So it means kinetic energy is 0. So here the kinetic energy will be 0, right? And at this point also the kinetic energy will be 0. So the graph will be like this way, right? Okay, this is the variation of kinetic energy, right? Now at this point the potential energy is 0, right, and at this point potential energy is maximum, right? So right, so this is for the potential energy, right? Okay, now whatever the variations that are been measured, it is in between the kinetic energy and the potential energy, right? So it means the upper one graph, right, that is a straight line. Okay, the graph of the straight line, that is the graph of total energy, right? So here I want to write it down. The total energy is constant, right? The total energy is constant. In another sense, total energy, that is equal to kinetic energy plus potential energy, right? At some point kinetic energy will be maximum, at that point potential energy will be minimum. At some point potential energy is maximum, at that point the kinetic energy will be minimum. So whatever the variations will go on, it will be in between the kinetic energy. At all points the total energy of the particle is going to be constant. At all points on the path the total energy of the particle is going to be constant, right? So this is what the graph is all about. Now let's move on, right, to the sums, right, whatever we have seen till now, to the sums of it. Okay, now sorry, the total energy of the particle, right, executing the SHM is proportional to what? Total energy, that is equal to kinetic energy, right, plus potential energy, right? Equation of the potential energy was half kx square, right? Equation of kinetic energy was half k, right, a square minus x square. Replacing this, half k a square minus half kx square plus half kx square. This thing is gonna cancel. So the equation of total energy, we are getting half k a square, in another sense half m omega square a square, right? Okay, m is constant, omega is constant, right? So the total energy is directly proportional to the square of amplitude. Total energy is directly proportional to the square of amplitude. A is the perfect answer for this specific question. A is the perfect answer for this specific question. Very simple. Okay, now starting from a origin, a body oscillates simple harmonically. See, now we are not going to see some basic sums related to it. No. Now we are going to see the sums that are already like they have been asked. See, weightage of this chapters is quite less. That's why the PYQs are less. But it's okay, right? We are going to deal with the energy and on all of those equations, right? Okay, so it will be quite easy, right, to understand the concept also and to grab the the clicks of the sum. Starting from the origin, a body oscillates simple harmonically. They have said particle is performing SHM with the time period of 2 seconds. Now see, time period, it is given as 2 seconds. Yes, it's good. So first of all, let's calculate the omega. Omega is equal to 2 pi by t. So it is equivalent to pi radian per second square. Okay, whether it is going to help or not, but we calculated it. What will be its kinetic energy? After what time the kinetic energy will be 75% of its total energy? So they have asked at what time the kinetic energy is 75% of total energy. So it means that, can I say kinetic energy that is equal to 75%, it means 3/4 of the total energy. What is the equation of the kinetic energy? That is half m omega square a square cos square omega t. What is the equation of total energy? Half m omega square a square, half m omega square a square, half m omega square a square. So we are getting cos square of omega t, that is equivalent to 3/4, right? So cos of omega t, that will be is equal to √3/2, right? So omega t we are going to get, right, pi by 3. Okay, I'm sorry, not pi by 3, it's √3/2 now, so it's pi by 6. Okay, so we are going to get it as pi by 6. Now omega t value is pi by 6, right? We need to calculate at what time, right? So what is the value of omega? It's pi into time. Pi is gonna cancel time at 1/6 seconds, right? At 1/6 seconds, the kinetic energy will be 3/4 of the total energy, right? The kinetic energy will be 3/4 of the total energy. At what time, right? So 1/6, at 1/6 seconds, right, the kinetic energy will be, right, 75% of total energy. A body executes simple harmonic motion Everything, see, whatever it is coming into the questions that I have delivered in front of you. Everything. A body executes simple harmonic motion. The potential energy, the kinetic energy, and the total energy are measured as a function of displacement. It's okay if they are measured in terms of the displacement, right? At mean position, x is equal to 0, it is a mean position, right? At mean position, the kinetic energy is maximum, right? Potential energy is minimum at the mean position, right? And total energy is constant at all points. Okay, sorry for that. What do you conclude from the graph, right? The frequency of the kinetic energy, potential energy, and the SHM. What do you conclude from the graph, right? What do you conclude from the graph? Just keep one thing into the mind, the frequency of the kinetic energy and the potential energy, right? Okay, one statement that I want to write in. The frequency on this, right? Many times the questions are asked. The frequency of the kinetic energy is always double the frequency of SHM. Right? Frequency, it means variations. In one oscillation, right, the variations of kinetic energies are twice at what the variations happens in SHM. Right? A is the perfect answer for this specific question. Right? Let's move on to the next question. A particle is executing the simple harmonic motion. See what kind of the questions, right? How we are using the equations of velocities in energies, right? Lots of students might be having the questions in their mind, right? Lots of the students are having the questions in their mind. Sir, why you are only giving us the questions of the energies? Why only the questions of the energies? Right, the total and mechanical and everything, it is there. So the reason behind it is, right, you are having you have done lots of practice questions, right, related to the fundamentals of the SHM, but this energy, it is going to, right, this will help us, right, in covering up the basic concepts also, right, and the high level also. Okay, so suppose if particle is executing the SHM, right, with the amplitude A, when the ratio of its kinetic energy and the potential energy is 1/4, displacement of its mean position is, see now, displacement from its mean position, this part is of the fundamentals of SHM. Ratios of kinetic energy and potential energy is 1/4, right? This will like force us to use the right concepts of energies. Ratio of kinetic by potential is given as 1/4. Right? We are aware of this is the equation of kinetic energy, right? This is an equation of the potential energy. But from how we are going to replace that equation, how we are going to replace that V. So here comes the concepts of fundamentals of SHM. So that's why question based on energies are kept, right? So that will help us, because this is a crash course, so that will help us also, right, to understanding or to cover up the all of these aspects of fundamentals of SHM. Now it is given as 1/4. Can I say kinetic energy is half k a square minus x square, that is equal to 1/4, and whole divided by that is half k x square. Half k is gonna cancel, right? So that is a square minus x square into 4, and that is equivalent to x of square. So can I say a square, that is equal to hold on, just hold on. Okay, so here 4a square minus 4x square is equal to x square. So 4a square, that is equal to, right, 5x square. So the position, right, is 2 under root of a, sorry, 2a by under root of 5. I'm sorry, not under root of a, 2, right, A by under root of 5. Plus or minus. At this position, the ratios of the kinetic energy and the potential energies are getting 1 by 4. Right. So what does it states? This is the mean position, right? X is equal to 0. At x is equal to, right, plus 2a by under root of 5, and x is equal to, right, minus 2a by under root of 5. At both this position, the ratio of the kinetic energy, right, with respect to the mean position, the ratio of kinetic and potential energies are getting 1 by 4. Right. So A is the perfect answer for this specific question. Let's move on to the next part. A mass 4 kg is suspended from a spring of force constant 800 meter. Executes the simple if the total energy of the oscillator is 4 joule. See, mass 4 kg, spring constant 800 Newton meter, total energy 4 joule. The maximum acceleration of the mass is what? Now here comes the fundamentals of SHM, but still in that the energy is involved, right? Still in that the energy is involved. Now see, total energy is 4 joule. So what is the equation of total energy? That is half m omega square a square, right? That will be equivalent to what? 4 joule, right? What is the equation of the total energy of the oscillator? That is equivalent to 4 joule. So what is the equation of the total energy? That is half m omega square. Can I say it is, can I replace this both as the value of K? Half K A square, that is equivalent to 4 joule. So K A square, that is equal to 8 joule, right? So here we are getting the amplitude A square as 8 by value of K. What is A square? That is equal to 8 by 800. A square, that is equal to 1 by 100. Amplitude, that is equal to, right, 1 by 10 meter. Amplitude we are getting as 1 by 10 meter, right? Or in another sense, amplitude that is equal to 0.1 meter. Now what is asked in question? Maximum acceleration. Okay, the equations will like immediately scrolled up in your mind, right? A is equal to minus omega square x. Magnitude A is equal to omega square x, right? Can I replace this equation, right? Maximum acceleration. Maximum acceleration always occurs when value of the x is getting A, right? Okay, so here we are getting value of the maximum acceleration as. Can I replace the omega square? Omega square, that is equal to K by M. So it's K by M into A. It is 800, mass is what? 4, and this is 0.1. So it is 80 by 4. The maximum acceleration is 20 meter per second square, right? A is the perfect answer for this. This includes the fundamentals of SHM and total energy. For a particle executing the SHM, the displacement x is given by this equation. Identify the graph which represents the variations of potential energy as a function. So that you are all aware of, and this thing you can do. So this question is homework from my side, right? You can answer this question beneath the video. Some might have seen this, right, and immediately guessed up the answer. Okay, that might be correct also. Okay, now let's move on to the most important, that is a Phasor method of SHM. Okay, the Phasor method of SHM. So students, it's a very simple thing, right? Let's move on to the Phasor method. Till now we have seen the concepts of periodic motion, oscillatory motion, right? All of the fundamentals of the SHM, the energies into the SHM. Now let's move on to the most important concept of the Phasor method. I must say, right, those students who have watched the lecture till now, right, I guarantee if Phasor method is used appropriately, then the lengthy sums can be solved in couple of minutes, and I'm going to show you some demonstrations of that. Right? The most weird and lengthy sum in which there is a highest possibility of getting wrong calculations or errors, right, can be solved in few steps, and some might be solved orally. But for that, right, Phasor method needs to be learnt, right? It needs to be learnt. Okay, now, so Phasor method, what actually it states? In the beginning, I'm going to write one statement in front of you all, right? The statement states that all the concepts of uniform circular motion, all the concepts of uniform circular motion are applied to SHM. Oh. Sir, that's wrong. That's wrong, sir. So how is it possible? How we can compare the uniform circular motion, right, to the SHM, right? And how you are going to prove that? Yes, we are going to prove that stuff, right? And you are really going to enjoy, right? Phasor method is like that. Those who are going to those who explains this method, right, at the very first attempt, it is impossible to understand the 100% content of it. At the very first attempt, it is impossible to understand the 100% of it, but yes, we are going to understand, because that sort of example I'm going to keep in front. There is one disk, right? This disk, there is a disk. A small ball or a bit is attached to the disk, right? Now, this disk is moving with the constant angular velocity omega, right? It is moving with the constant angular velocity omega. Constant angular velocity omega. It means I can say that this ball is performing the uniform circular motion. Is it clear? This ball is performing the uniform circular motion. Is it clear? Yes, is it clear? It is clear. Disk, a ball attached to it, it is moving on the circular path, right? Ball attached to it, it is moving on the circular path, right? Angular velocity of the disk is constant, so same for the angular velocity of the ball is constant. So this is a uniform circular motion. Sir, where is the SHM? Yes, it is going to come. Right? It is going to come, don't get worried. Okay, let's play some, okay, light here. Light is having this kind of reflection, not reflection. The rays are coming out like this way, right? The rays are coming out like this way. At the bottom, we are having a floor. Obviously, the light is going to, right, strike on the floor. Now, what will happen? Right? What will happen here? The projection of this ball, in another sense, shadow of ball, right? You can see the shadow of the ball on the respective floor. If the ball is at the position A, its shadow is at this position A. If the ball is at this position, the shadow is at this position B. If the ball is at this position C, right, the shadow is at this position. Again, if the ball is at this position, the shadow is at this position. Again, if the ball is moving at this position, the shadow is at this position. You can understand the ball on the disc is performing the uniform circular motion, but its shadow is performing the SHM. disk uniform circular motion, shadow SHM. That's an example of it. The best visualization that we can compare, right? Yes, all the concepts of the uniform circular motion are applied, right, to the SHM. Again, I'm writing that statement. All concepts of uniform circular motion ball is attached to the rim, right? It is moving on, right, with a constant angular velocity, but its shadow, see, it's a uniform circular, or that's SHM, right? Okay, now see the equation, the displacement equation of the SHM is x is equal to a, right, cos of omega t, right? Velocity equation is a omega negative, right, sine of omega t, right? Acceleration is equal to negative a omega square, right? Okay, cos of omega t again. As I said, the value of the cos differs between -1 to 1. Value of the sine differs from -1 to 1, right? So for SHM, see, SHM is a kind of a to and fro motion, right? I told into the previous part of this session, right? The sine, the presence of sine and cos and its value that is changing between -1 to 0, 1 is not only the reason behind this equation that they are represented for SHM. This is not only the reason, right? If I'm talking about the position, right, the maximum displacement is A, the value of A, right? Okay, the value of the X, that is position at any time t, is varying between -A to A, right, in between, right, crossing from 0. Okay, so similarly, not only see cos, sine, you can see in this all of those equations we are having the trigonometric functions sine and cos, right? So these are not only the reason behind it. These are not only the reason behind it, right? Not only the reason behind it. Okay, these are not only the reason behind it. The phasor is most priorly included in that. Right, we wrote down that equation. Now see, now this, see, suppose, okay, you can understand, see, suppose if the light is kept on this part, okay, then particle is performing the SHM on this way. So for this displacement equation we can write it down, x is equal to a cos of omega t, right? Now suppose if I'm changing the position of the light, this is a great confusion that students are facing. Suppose if I'm changing the position of the light, if light are kept on this way, right, now the shadow will perform the SHM into the vertical direction, right? Shadow will perform the SHM as it is performing in the horizontal part also, right? But the light projections will fall like this way. Light projections will fall like this way, right? Okay, and for this we are having the equation of SHM as y is equal to a sine of omega t. This is the difference, guys, right? This is the difference, guys, right? This is the difference. Okay, y is equal to a sine of omega t. Okay, so if the particle is moving onto the circular path performing the uniform circular motion, so it means, right, the light projections, right, the shadow of the particle is performing SHM. It means all of those concepts, right, of the SHM we can apply to the uniform circular motion. And now let's see what actual the phasor is. Phasor. If I want to define the phasor, then it is a rotating vector. As I used to say in all of my lectures, in the amples of resources, right? Okay, hundreds of definitions are given, but simply if I want to define the phasor, then it is the rotating vector, right? You can see into the visualizations also, right? Okay, suppose, see, this is a path. Sir, you said that uniform circle, all the concepts of the uniform circular motion, right? It is an analogy that all the concepts of the uniform circular motion can be applied to the SHM. Sir, it's okay, we understood. We understood, but right now lots of shortcuts are going to come. Now this half an hour, the next half an hour will be completely full of shortcuts. Full. If for the equation y is equal to a sine of omega t, right, just mind down, this will be plus a, this will be minus a. For a motion, right, for a vertical SHM, this is the criteria. If you want to move on for the horizontal SHM, see, vertical SHM, it means that, see, horizontal SHM is like this way, right? Horizontal SHM is like this way, right? Horizontal SHM is like this way. So, okay, so one is the horizontal motion, second one that is, sorry, there was a technical glitch. This is for horizontal SHM, this is for vertical. For vertical, we are having this is plus a, this is minus a, this is the mean position, right? For horizontal and vertical, mean position is same, right? For horizontal, this will be plus a, right? This will be minus a. What is the phasor? Phasor will be the rotating vector, right? Okay, that rotates with the constant angular velocity omega. Phasor is rotating vector that rotates constant angular velocity omega, that rotates with the constant angular velocity omega, right? That rotates with the constant angular velocity omega. Okay, so in this case, it rotates with the constant angular velocity. Okay, now let's move on to the understand this thing into the detail. Okay, see, I am talking about, right, the SHM into the vertical direction, right? We are going to take that example to understand this topic into this detail, right? Because using this topic, I think, right, the lengthisms are going to solve into the very few steps. Okay, see now, for vertical, this will be plus a, this will be minus a. Suppose if I am to represent the phasor first, suppose, right, if I want to draw this phasor diagram for the equation, y is equal to a sine of 2 pi t, a particle that is performing the SHM, and that equation is represented by this. A is an amplitude. What is the value of the omega? Omega, that is equal to 2 pi, right, radian per second. Omega, that is equal to 2 pi radian per second. Okay, omega, that is equal to 2 pi radian per second. So this is plus a. Now initial phase is 0. It means what? Phasor starts from t is equal to 0. Initial point for phasor, right? Now it is rotating with a constant angular velocity 2 pi radian per second, right? So in 1 second, it is completing the entire circle. In another 2 seconds, it is continuously like completing the entire circle. So it means after time t1, phasor is in this position. After time t2, the phasor in this position. After time t by 4 or some t time, right, phasor is at this position. then it will move on to this position, it will move on to this position, it will move on to this, and final to this. Like this way it is rotating continuously. Now students are getting confused. Sir, basically there are two ways of phasor rotation. One into the anti-clockwise direction, into the clockwise direction. While moving on into the anti-clockwise direction, right, the answers will differ, right, as compared to moving on into the clockwise direction. So what actual the correct method is. So for that I want to write it down. Phasor always moves into anti-clockwise direction. Phasor always moves into the anti-clockwise direction. Always. Right? Why? Because angle. There is one property of there is one noteworthy point of an angle. When we saw this thing into the units and measurement, there is one noteworthy property. What is that? Angle is always calculated with respect to the positive x-axis and in anti-clockwise direction, double quotes. Again, I am highlighting this statement. Angle is always calculated with respect to the positive x direction into the anti-clockwise direction. Same way, right? The same thing is for phasor. It is always calculated with respect to the positive x-axis, right, and into the anti-clockwise direction. It always rotates. As I said, phasor rotates with the angular velocity omega, yes, but it always rotates into the anti-clockwise direction. Phasor, right? Okay, so suppose, let us take an example. Okay, now suppose in question it is written a particle is performing the SHM, y is equal to, right, 10 sine of 2 pi of t plus pi by 3, right? If this is an equation of a particle that is performing the SHM, draw the phasor diagram. This kind of the question. See, basically 3 to 4 kind of questions are there, right? And in the phasor method is also useful into the cases, right, where superposition of the SHM is also, right, studied. Okay, so now suppose if I want to draw the phasor for this, right, so this is a phasor diagram. Okay, see, 10 is an amplitude, so this will be the value plus 10, right, this will be the value minus 10. This is the y, it means the SHM is in the vertical direction. What is its path? This will be the path of the SHM, right? Slowly we are going to calculate the velocity into the very rapid manner. Slowly we are going to calculate, right, okay, the acceleration into the very rapidly. I'm going to show you all the shortcut for this, but first of all, let's see some basic sums related to it, then we are going to see some shortcuts. Initial phase angle is pi by 3, right? So this is pi by 3. This will be the initial point of the phasor from which it is going to start to rotate with the angular velocity omega. This is in phasor diagram, right? So let's move on to the sums related to it. Okay, then you are going to understand this stuff. Now see, first question. The figure shows the circular motion of the particle. The figure shows the circular motion of the particle which is at the topmost point only on the y-axis and t is equal to 0. The radius of the circle is also given. The simple harmonic motion of the x projection, see, it's mentioned. We need to identify the correct equation. It is given x projection, it means that, right, it is given the x projection, it means that this is the motion, this is the path of the SHM of the particle. This is the path of the particle, right, performing SHM. Now, at t is equal to 0, initial position is this. It means particle is starting from mean position, right? Particle starts from mean position. Particle starts, right, from x is equal to 0. It means initial phase is 0. Time period is given as 30 seconds. So time is equal to 30 seconds, 2 pi by capital T, that is equal to 30 seconds, T is equal to 2 pi by 30. I'm sorry, yaar. 2 pi by omega, right? So this will be the angular velocity of the rotating vector phasor. Now, if I want to represent this equation, then x is equal to a, right? X is equal to a. You can see this, right? Okay. Now, what is the max displacement? It is given as b, right? B is the max displacement. You can see the radius of the circle. The radius of the circle is its amplitude and it is the max displacement, right? Initial phase is 0. So can I say the equation of the particle, right? X is equal to a sine of omega t plus phi. Initial phase angle is 0. Amplitude is b, right? Initial phase angle is c, 2 pi by 30 into t, right? This is the correct equation of the SHM of the particle using phasor, right? A is the perfect answer. Now let's see the magic. Particle executes SHM if the time taken by particle to minus a to a by 2 is 4 seconds. Its time period is what? Now see. This is positive A, this is negative A. Particle is moving on from minus A to plus A by 2. See, as I said, phasor always rotate into the anti-clockwise direction. Minus A by 2 comes here, right? Okay, minus A to A by 2. I'm sorry, it's moving on from minus A to A by 2, right? So see, minus A is here, right? A by 2 is somewhere here, right? So this is an initial position on the phasor, right? This is a final position on the phasor, right? I'm going to show you all the difference. What is an actual method and how a phasor is resolving and saving a time, right? How phasor is resolving and saving your time, right? So here I think okay, so in between initial and final points, right? Okay, the phasor always rotates into the anti-clockwise direction. So suppose it is moving into the anti-clockwise direction, right, with the angular velocity omega, right? The difference, the time difference between the initial and final points, it is given as 4 seconds. Now, what is an actual method? Y of a sine of omega t plus phi, right? First, we are going to replace for minus a, and then we are going to calculate for t1. Second, we are going to replace for a by 2, then we are going to calculate for t2. In both of the cases, we are going to replace, right, the value by the 4 seconds, and long calculations we are going to do to find the time period. But this thing can be solved easily by means of phasor, right? How? What is the phase difference? Just always calculate the phase difference between these 2 points. This is pi by 2, right? Okay, always move into the anti-clockwise direction, right? This will be pi by 6, right? One is pi by 2 and second is pi by 6. What is an actual phase difference? The phase difference between the initial points and final point, that will be pi by 2 plus pi by 6. So that will be equivalent to 2 pi by 3. It is moving on. See, we need to calculate the time period, and it is moving on with a constant angular velocity omega. A very simple step. Omega is equal to phase difference by delta t. Delta t is given as 4 seconds, right? Okay, so omega, that will be equivalent. What is the phase difference? 2 pi by 3 whole divided by 4 seconds. What is the value of omega? 4 omega, that is equal to 2 pi by 3, right? So it will be 4 into 2 pi by capital T. Omega I am replacing by 2 pi by capital T. That is 2 pi by 3. This 2 pi is going to cancel. T is equal to 12 seconds. This is the time period of the SHM. A very simple calculation. And the very first attempt, I can understand it will take some amount of a time to, right? Okay, to understand, to grab this thing. But if you have done this, right, I assure you the difficult sums can be solved within few steps using just a single formula. Okay, this is the same sum, it has been repeated. Okay, now see now how we can calculate, right? Okay, just by the geometry we can calculate the velocity and acceleration at the each point. See, suppose this is a 10 centimeter negative, the amplitude, this is a positive 10 centimeter as the amplitude, right? Suppose a particle that is performing the SHMX, that is equal to, right, 10 sine of 2 pi t. We need to calculate the velocity, right? We need to calculate the velocity, right, at x is equal to 6 centimeter. We need to calculate the acceleration at x is equal to 6 centimeter. Again, that long formula based calculation. No, we are going to solve it quite easily using Phasor. This is plus 6 centimeter. This is an initial position of the particle. Right? This is a final. Very simple thing. See, this is a radius. It means it is 10. This is 6. What will be this angle? Right? It will be 10 of 5. Right, that will be equivalent to 6 by 10, so that will be equivalent to 3 by 5, that will be equivalent to what? 37 degree, right? Okay, so this will be 37 degree, this angle will be 37 degree. At this position, as I said, all of the concepts of the uniform circular motion can be applied to this. So velocity, for a uniform circular motion, velocity is always tangent to the path. There are two components, one in this direction, one in this direction, right? You have to just calculate. Suppose this is 37, this is 37, right? This is 53. This component will be V cos of 53, V sine of 53. This will be your answer because it is lying parallel to the path, right? See, now acceleration, the radius is 10, right? Okay, this is 37. Now acceleration always acts towards the center and it is moving on the circular path, then that we can compare it to the centripetal acceleration. This is the component A cos of 37. This is the component A sine of 37. The component that is acting parallel to the path will be our answer. So at 6 centimeter, this will be our acceleration and this will be our velocity. This is as much easy as you are thinking right now. Yes. This one is homework from my side. It is a very simple sum based on the Phasor. Now, I'm going to show you all one shortcuts, right, on the base of the time period of the SHM. I'm going to show you all some shortcuts on the base of the time period of the SHM. Right now, let's move on to the cases of the time period. You all are aware of, right? Okay, before that, let's have some water. Okay, so you all are aware of, there are some cases, right, in which the time period of SHMs are asked. Like suppose This is a spring. This is mass M. If gently push is given, a gentle push is given, then obviously it's going to start performing SHM. What will be its time period? T is equal to 2 pi, right, under root of M by K, correct? This is an actual formula. Now, suppose if two springs are connected in parallel, right? What will be the formula of time period of SHM? T is equal to 2 pi under root of M by K equivalent. T is equal to 2 pi under root of this thing, all of these things, right? Okay, some part of like this concepts we have seen into the work energy of power while dealing, right? We have seen that when what will happen when springs are connected in series, right? What will happen when springs are connected in parallel? So in parallel, K equivalent, right, that is equivalent to K1 plus K2, right? So final time period equation of the SHM is under root of M by K1 plus K2, right? Suppose this is a case of the parallel connection of the springs. Suppose the series connections of the springs it is given. This is a spring of the spring constant K1, another spring of the spring constant K2. Right, and they are connected in series. This is K1 and this is K2, right? One it is connected in parallel, second it is connected in series. So in this case, K equivalent, right, we are having when they are connected in series is K1 K2 whole divided by K1 plus K2. So the time period for this, that is T is equal to 2 pi under root of M whole divided by K1 K2 whole divided by its K1 plus K2. This is the time period of the SHM. This is a very basic formulations. Now in this, right, 2 to 3 methods are there, right? Okay, sums based on this in JEE mains and advanced they are asked, right? A lots of pulleys and spring mass systems are given, a complicated systems are given, and we need to calculate the time period of the SHM of the particle. Right, we need to calculate the time period of the SHM of the particle, and today we are going to see that stuff into the very simplified form. Shortcut I am going to show you in front of you all. The mains and advanced level sums based on this shortcuts, right, we are going to solve. Now let's see what actual the shortcut is. Right, today I am going to give you all the solution for a right most critical problem. Let's see. Right, suppose one arrangement it is given like this way, right? One arrangement it is given like this way. Again, we need to calculate the time period for the SHM. Pulley mass system is there with springs attached to it, right? Okay, for this a displacement method is there and blah blah, lots of things are there, but I'm going to provide you all a shortcut, direct shortcut, no need for anything, and that shortcut is applicable for everywhere. Right? The shortcut states the formula of the time period is T is equal to 2 pi under root of M by K equivalent. Right, this is a formula that you need to remember for all of those cases. What will be the value of the K equivalent? That will be K of spring tension on block by tension on spring whole square. Sir, suppose if it is about more than one springs, then how you are going to solve? I'm going to show you all, right? And most critical sums we are going to take. Okay, just to remember these two things, right? And now we are going to solve the sums. Let's see. First, Suppose if it is arrangement, it is given like this way. All of those critical sums I'm going to take. The arrangement is like this way. Right. This is a spring of the spring constant K. This is of the spring constant K. We need, suppose if the gentle push is given to the block, then we need to calculate a time period for the SHM of the block. What will happen? Right. What will happen here? Right. It's a very simple thing. Right. What will happen here? Again, the displacement we are going to calculate it. No. Simple one shortcut. See. First of all, what will be the tension on the block? T. What will be the tension on this spring? T. What will be the tension on this spring? 2T. Two springs are there, na? N numbers of, for this shortcut, N numbers of springs are there. Consider all into the series. Right. Now see, very simple thing. For spring 1, this is spring number 1, this is spring number 2. Right. Can I say K1? That is K for spring, right, into tension of block by tension of spring whole square. Right. So can I say K1 that is equivalent to what? K of spring is K. It's K. What is the tension of block? T. Tension of spring T whole square. Can I consider this as equation number 1? Yes. For spring 2. Right. Can I say K2 that is equal to K of spring into tension of block by tension of spring whole square. What is tension on block? T. Tension on spring 2T. So can I say K2 that is equal to K, right? Tension on block T, this is 2T, right? Whole square. So K2 that will be equivalent to K by 4. Can I consider this as equation number 2? Two springs are there, na? Using the shortcut, we calculated that, but now consider both in series. Whatso arrangement it is given, consider both in series. What will be the K equivalent? That will be equivalent to K1, K2 whole divided by K1 plus K2. Right? So it will be K dot K by 4 whole divided by 5K by 4. So this K by 4 is going to cancel. K equivalent we are going to get K by 5. What is the time period? T is equal to 2 pi under root of M by K equivalent. So T is equal to 2 pi under root of 5 M by K. This is the time period of the oscillation for the object. Shortcut. Let's take another sum to understand this stuff. Suppose if this arrangement it is given. This is K, this is K, this is K. We need, suppose if the gentle push is given, we need to calculate the time period for the SHM of this blocks. A most weird arrangement, right? I'm damn sure, suppose if this kind of the arrangement is asked into the JEE mains or right advanced level examination, you are going to, right, I'm damn sure you will fail to apply the regular method, but this shortcut is going to help, because in this kind of the examinations, right, we are not moving on to the theoretical approach, right? That's why. What is the tension on the block? Suppose here the tension is T, 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 and T. Right? Here we are having 2T, here we are having 2T, here we are having T, and here we are having T. The tension on the block 6T. How many springs are there? We are having 3 springs. Right? We have to consider all in series, but calculations are individual. For spring 1, right, K1 that is equal to K of spring, that is K, tension on block by tension on spring, right? All of the springs are having the same 2T, 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 right? Okay, so it's tension on block by tension on the spring 6T, right? Whole square. This is gonna cancel, right? So it is equal to K by 9. For spring 2, again the calculation is going to be K by 9. For spring 3, again the calculation is going to be K by 9. Consider all in series, right? 9 by K, 9 by K, right? And 9 by K, okay? And 9 by K, that is 1 by K equivalent, right? Okay, so what will be the K equivalent? That is K by 27, right? What is the time period? T is equal to 2 pi under root of, right, 27 m by K, right? Okay, so it's 9 3s are 27. T is equal to, okay, 6 pi under root of 9 into 3, so it's 3 m by K. This is the time period of the SHM of the block. A very critical case you are going to solve using sums. So this is how the time period of the right SHM is being calculated. Right, now let's move on to the most important and the last point of this chapter. Right, okay, see, according to the JEE and NEET point of view, whatever it is coming, I'm showing you all in front. Okay, now let's move on to the most important thing, and that is the last part of this chapter, the damping force and the forced oscillations. Right, the damping force and the forced oscillations. Okay, let's move on to that. So students, into the case, okay, so students, into the cases of the angular SHM, right, the two most important things are there. First, the comparison of the angular SHM with an SHM, and in some of the cases the time period of rigid bodies is calculated, right? Time period of the oscillations of the rigid body. Now let's see, we are going to see that stuff. Okay, now see, angular SHM. See, without wasting the time, we are going to compare the angular SHM with the SHM and going to understand this situation. See, suppose if I'm taking an example of a pendulum, right? This is in pendulum and this is in a bob connected to it, right? Okay. Now suppose if the gentle push is given to the bob, if the gentle push is given to the bob, then obviously it is going to oscillate, right? On the either side, right? This is going to be the maximum displacement, right, of the, this is going to be the maximum displacement, right? In another sense, maximum angular displacement of particle, right? Maximum angular displacement is phi. But with respect to time, suppose at t is equal to 0, the bob is released. With respect to time, slowly, the angular displacement is getting increased, right? The angular displacement is getting increased. So, if I'm talking about any time t, the displacement is theta, right? The displacement is theta. And at that time, the angular, or you can say, we can say it as an x, and this is amplitude A, right? So can I say x, that is equal to L of theta, and amplitude, that is equal to L of phi, right? For SHM, restoring force is responsible. For angular SHM, restoring torque is responsible, right? Here one restoring torque is there. Suppose this is mg, right? Here we are having the component mg sine of theta. This is going to create one restoring torque because it is included into the, say, in cases of the rotational motion, torque is only responsible for a particle to come back to its original position. In SHM, it was a case of the translatory motion, so that's why restoring force was responsible, and in the cases of the angular SHM, restoring torque is responsible, right? So yeah, if I'm talking about for bob, the equation of SHM is represented as x, or in another sense, I've taken it as an x, so I'm taking it as an x, and that is equal to a sine of omega t plus phi. So can I replace x as L theta, a as L of phi, and that is sine of omega t plus phi. So L will get cancelled out, so theta is equal to phi sine of omega t plus phi. So in the case of the angular SHM, this is angular displacement, right, at any time t. Phi angular displacement that is maximum. In case of SHM, we were having x or y, that is equal to a sine of omega t plus phi. Here a was maximum displacement, here it is phi is maximum angular displacement. Here x what position at any time t, here this is angular displacement at any time t. This is what an actual difference between SHM. Right. Now suppose we got this equation, right? See, the angular displacement at any time, that is phi sine of omega t plus theta. Now differentiating this equation with respect to time, what we are getting, that is d theta by dt, angular displacement with time, that shows the case of angular velocity, and that is equivalent to what? Phi, right, into omega, and that is cos of omega t plus phi. This shows the case of the maximum angular velocity, right? Or you can say the angular velocity amplitude. Again differentiating this equation with respect to time, right? What we get, alpha, that is equal to minus omega square theta. This is the condition, right? We were having one condition. Say if the particle is satisfying this equation, a is equal to minus omega square x, we can say the particle is condition for particle to perform SHM, right? Similarly here, alpha is equal to minus omega square theta, condition for particle to perform the angular SHM. This is only the differences, right? Now with this, one another example is just suppose how to calculate the time period for this kind of things, for the rigid bodies, right? Again, for this I'm taking one example of a bob. Suppose this is a bob, right, and it is having some angular displacement with respect to time, right? Suppose this is at the max position, this is phi, right? Okay, I must say into the previous one, thetas and everything are colliding. Okay, this is not phi, we are changing the angle as alpha because it is of the SHM. We are changing it as an alpha, right? I'm sorry, we are changing it as an alpha. Okay, this is an alpha because I think more than two symbolic notations are there. That's why we are changing it as an alpha, right? Okay, here also we are changing it as, it's okay, alpha. Okay, because three angles are there. Now one, this angle is for the bob who's performing the SHM, right? This theta is angular displacement at any time, and this phi is a maximum angular displacement. These three are the different phase angles, sorry, different angles, right? Okay, now mg is acting into this direction here, mg sine phi. This is responsible, the restoring torque, right? The restoring torque is responsible for particle to perform angular SHM. Restoring torque is right of a particle is, right, okay, responsible for. So can I say that restoring torque is directly proportional to theta as force is directly proportional to displacement? Removing the proportionality sign, can I say torque is equal to k theta, right? Okay, on the opposite side, If torque is equivalent to negative k theta, what is the condition, right? Can I say this torque is directly equivalent to I alpha also, right? So it means I alpha is k theta, right? So here what happens, I'm sorry, just hold on, right? We are going to do this derivation. Okay, see, now I alpha is directly proportional to k of theta in terms of the magnitude, right? Okay, so I, can I say alpha, right, that is equivalent to k by I of theta. Can I compare this to, suppose if you are keeping a negative sign here, can I compare to minus omega square theta, that is k by I into theta, negative, right? So here what we are getting, omega that is equal to k by I, right? So here 2 pi by t, that is equal to k by I, right? Here t is equal to 2 pi under root of, right, it's omega square, na? So it will be under root of I by k, where I is the moment of inertia and torsional constant, k is, or you can say proportionality constant, right? K is proportionality constant. This is how, right, the time period of the, right, SHM has been calculated. Okay, the time period of SHM is calculated. So this is how, what an actual difference between, right, the angular SHM and SHM, right? Okay, there are some important formulas that I showed in front of you all. Okay, now with this, let's move on to the next topic, that is a damped force and force oscillation, the last topic of this session, right? So students, now let's move on to the most important part of this chapter, and a very easy, because at some of the channels, right, this thing has been kept right into the very different way, right, that seems to be quite complex, right, for you all. But right, the noteworthy and important points, right, from the topic damping and forced oscillations, right, we are going to discuss the most important stuff, right? Okay, from the exam point of view, right, not the complicated examples I'm going to show you all in front, not as much, right, high level sums, no, a very simple thing into the very appropriate manner and the useful formula, that's it, right? In Hindi it is called as na idhar ki baat na udhar ki baat, seedhi baat, no bakwas, right? Sprite clear hai. So it is not any kind of the promotional content here, right? No, it is just a very simple thing, right? We are going to discuss what is the damping and the forced oscillation. Before moving on to the damping and the forced oscillation, I want to show you all one simple example in front. This is the mean position of the particle, x is equal to 0, t is equal to 0. It is a mean position, right? Now, from the mean position, a gentle push is given and it is released, right? Gentle push it is given and it is released. Now, what happens here, right? A gentle push it is given and it is released. Now, what happens here? Now, see here, suppose this is a spring constant of now. Is there any kind of the dissipative forces it is present in the surrounding? Generally, all of those cases we are considering, right, into the vacuum, right? I'm not saying about the gravity free space, right? But in environment, no atmospheric pressure is acting and no air resistance is there, this kind of things are there. But here, if I'm talking about the practical terms, first, are surfaces perfectly smooth? In the beginning part of the session, we consider the surface as smooth. Practically, is it possible that for any surface mu is 0? No air resistance, no damping. Is it possible? I must say no. Right? To understand the concept into the convenient manner, we always used to consider as no energy loss. We also considered one most important point, that total energy of the SHM at all points, right, is constant. Is it for sure? Because while considering the total energy of the constant, right, work done by non-conservative, work done by external, that is equal to delta K plus delta U. Did we consider any work done by the non-conservative forces? Generally, the dissipative forces are considered into the non-conservative. Did we consider that? No, we consider it as a zero. Did we consider any external agent? No. That's why the total energy of the SHM is conserved. It is constant at each and every point. But here, damping means there is the presence of any external force. If I am talking about SHM, in absence of any external force, in absence of any external, right, force, what is the responsible thing for the SHM? Right, F is equal to the restoring force is a responsible thing, right? So here, if I am replacing M into A, that is equal to minus Kx, M into dV by dt, right, that is equal to minus Kx, okay? Now here, if I am replacing M into d square x by dt square, right, that is equal to minus Kx. It's M d square x by dt square, right, plus kx, that is equal to 0. This is the differential equation of the SHM that states there is no presence of any kind of the damping forces. If there is no presence of damping force, then and then F is equivalent to minus kx. Here, actually it should be any dissipative, right, or any damping force is there. If this is 0, then and then F is equivalent to minus kx, and we are considering the pure SHM. The ideal situation in practical life, it is not possible. Now, what is the role of this damping force? We consider the total energy as constant at all points. Damping force, right, what does this damping force does? Let's analyze this example. The day-to-day life example of this swing, right? Okay, so in SHM, F is equal to minus kx, differential equation M d square x by dt square plus kx, that is equal to 0. No damping force is present, right? The next point, total energy is constant at all points, right? Total energy is constant at all points, but damped oscillations, total energy decreases, right, with respect to time. Total energy decreases with respect to time. You can see one example, swing. Our day-to-day life example of the park, we used to move on with siblings, or generally if I'm talking about myself, then I used to move on to the park with my daughter, right? Okay, with my daughter. So whenever she used to swing, right? Okay, every time, if I'm if I'm giving her a force once, then for a while, it starts swinging and slowly it stops. Is there any kind of the presence of the damping force? Yes. Is there any kind of the presence of the damping force? Yes. Is there any kind of the resistive force acting? Yes. If resistive force is not acting, then on applying the force once, that swinging should continue till infinite time. But is it happening? No, it's not happening. Is it happening? No, it's not happening. Is it the same thing? No. So what happens here? Right? One resistive force is acting that slowly acts against the motion of the particle. And that decreases the total energy with respect to time. And that force that is acting, that dissipative resistive force acting, it is known as a damping force. Damping force is always directly proportional to the negative of the velocity. Why? It always opposes the motion. always opposes the motion and try to stop the SHM. And for that reason, the energy, the total energy is decreasing with respect to time. The graph of the total graph of the total energy like this way, but it's okay, right? Actually is like this way. Right, so it always, the damping force always opposes the motion. The formula of the damping force, it is 9, right? Now suppose if I'm talking about the same example, right, this is a spring attached and this is a mass m, right? Here the, let us take an example, kx is acting into this direction, and obviously in this direction there is a damping force that always opposes the motion of the particle. Right, there exists a damping force, right, that always, right, opposes the motion of the particle, right? So here the differential equation we can represent it as minus kx minus bv. This is the part of the damping force, right? Okay, so here the differential equation is d square x by dt square plus kx plus bv, that is equal to 0. Right, and among them b, that is known as damping constant. Now in this presence, right, okay, the actual, see, let's compare the equation of the SHM and the damped oscillations. In the equation of the SHM, I must say, in the equation of the SHM, right, and the damper, in the equation of the SHM, x was a cos of omega t. In the damped oscillation, x, it is given as a 0 e raised to minus bt by 2m, right, and cos of omega t. This is how the displacement is varying with respect to time. Right, here the total energy is constant. Right, here the total energy decreases with respect to time. Here the maximum displacement is this. Here the maximum displacement is calculated by this formula. This is an actual difference between the damped oscillations and the actual SHM that we have studied till now. What about the forced oscillation? A very simple concept. Suppose, let us take a very simple example. If the gentle push it is given, right, a gentle push it is given, right, a gentle push it is given, slowly the object is starting performing the SHM, and as because of the presence of the damping forces, right, as because of the presence of the damping forces, slowly the energy is getting decreased, and after infinite amount of the time, right, after infinite amount of the time, right, okay, after infinite amount of the time, slowly it stops. Now what happens here? If we want to continue its motion, then there is a need of an external forces, and here comes the concept of the forced oscillation. If we want an object to continue its SHM, right, we need external forces, right, and here comes the concept of the forced oscillation, right. If the total energy is slowly decreasing with respect to time, slowly it is decreasing with respect to time, and finally it is getting to 0 and object stops. So in that case, I want to tell you all, if energy is decreasing and the rate of decreasing is not uniform, in damped oscillation, right, rate of decreasing in amplitude, rate of the decrease in amplitude to stop, it is a is equal to a0 e raised to minus bt, where b is a damping constant. This is the, right, it is not uniform. So suppose if this is a not uniform thing, then we need a external force that should also be not constant in nature, right? So in this case, we need external force that should not be constant in nature. So for that reason, right, see, now you can see in the swinging, the same example we are taking. Suppose if I am applying, my daughter is sitting on that thing, right, and if I'm applying a force, right, and it starts swinging, after some amount of the time, the total energy is slowly getting decreased. Right, now there comes the situation, if I want to maintain, right, my daughter, right, she screams, "Papa!" I got a signal, I need to apply the force. Now what I used to do, first I applied a high amount of the force, then low amount, then now here comes the situation when, right, the particle is, right, when the particle starts, right, comes in its original state, then what I used to do, right, that is the difference, right? I'm comparing this thing to the day-to-day life examples, right? So it is easy to understand. So here, right, whatever the amount of the net force is there, it is minus kx, damping is present minus bv, plus one external force that should be, right, vary with respect to time. That kind of the force we need to apply. Here comes the concept of the forced oscillations. We are trying to apply that kind of the force that, right, maintains the state of the SHM. Slowly it will increase the total energy and can reach up to the, right. So this will increase the total energy, right, with respect to time to peak value. Now here comes the situation resonance. While crossing on from 0, see, it was swinging, particle was performing the SHM, as presence of the damping force is slowly it reaches to 0. Now one external force of this value is applied. Now slowly, right, it is trying to gain, okay, some amplitude. Now it is reaching to the high value, okay, finally it is reaching to the peak value. So this is journey from 0 to peak. When external force is applied, it is journey from, right, a particle is not, now on applying then external force, the particle is not, it is not trying to attain to maintain the state of the SHM. No, now the amplitude is going to get continuously increased. So in that case, one situation arises. First of all, I am going to write down the differential equation, m d square x by dt square plus kx plus bv plus f0 sine of omega t plus phi. Now on applying an external force, one situation arises where the frequency, right, of oscillator matches the natural frequency. Suppose initially the frequency of the SHM was 2 pi. Now here comes the damping force. Slowly it decreases to 0. Now again external force is applied. Now value is increasing from 0 to pi by 2, pi by 3, pi by 4, like so it is increasing, it is reaching to pi. Finally it is reaching to 2 pi. So whenever the external force is applied, there arises a situation, right, where the particle is about to oscillate with its natural frequency with which it was oscillating without damping. That situation, it is known as resonance, and at that point of time the particle, right, is oscillating with the frequency, the amount of frequency is known as what? The resonant frequency, right? This much part is only there, and in this also in 2002 and 2004 and 5 sums are asked. Since 5 to 7 years questions based on this are not asked. So it's a very simple thing we are going to see, right? When an oscillator completes, see, the question is asked in 2002. It's a very simple concept, but at some of the channels, right, this thing are kept into the quite complex way, and with this lots of sums of NLMs and everything are kept extremely, I must say, right, whatever the things I'm presenting in front of you all, this much is only needed, not more than that, right? Apart from this, right, lots of things are there. Okay, when an oscillator completes the 100 oscillation, its amplitude reduced to 1/3 of the initial value, right? On completing the 100 oscillations, right, amplitude reduces to 1/3. On completing the 200 oscillations, what will be its new amplitude? Now see here, amplitude is getting reduced. It means by seeing the question, right, we are easily able to understand, this is a case of the damped oscillations, and we need to apply this equation. A is equal to A0 e raised to minus bt. So what happens here? A0 by 3 is equal to A0 e raised to minus bt, right? On completing the 100 oscillations, right, this thing is happening, right? So e raised to minus bt, that is equal to 1 by 3, right? So bt value, that is equal to ln of 3. And I consider this as equation number 1. Yes. What will happen on the completion of the 200 oscillations, right? What happens on the completion of the 200 oscillations, right? Okay, when an oscillator completes the 100 oscillation, okay, the time period of the one oscillation is t. The time period of the one oscillation, right, it is t. So let's compare this to equation, right? Okay, so here first of all, can I say A0 by 3, that is equal to A0 e raised to minus b into 100 by v. Can I consider this as equation number 1, right? Now okay, this much is enough, but I think this much is enough, right? This much is enough, right? Now okay, now let's solve this. Okay, now for the 200 oscillation, can I say value of A is A0 e raised to minus b into 200 by v, right? So taking ratio of 2 by 1, right? So we are getting A whole divided by A0 by 3, and that is e raised to minus 100b whole divided by e raised to minus 200b by v. So solving this, we are getting A is equal to A0 by 9, right? D is a perfect answer for this specific question. Okay, same equation we are going to use, but it's okay. So simple this equation. On this equation the questions are asked. See, again it is asked in 2003. In the case of the forced vibration, the resonance peaks are very sharp when, see, when there is one resonance curve, right? When the resonance curve is quite sharp, it means that on application of an external force, right, the frequency of the oscillator, we have discussed the resonance situation. The frequency of the oscillator is trying to match the natural frequency. It is matching the natural frequency of an particle that is performing SHM in absence of damping. But damping is in that situation, I must say, right, we can't completely avoid the damping part. So for that, it is negligible, right? So in the case of the resonance, when the external force is applied to a particle, slowly the frequency of an oscillator is increasing, and at one moment it is reaching to the, right, at one moment it is matching up to the natural frequency. At that point a resonance occurs, and in resonance condition damping force is quite small, right? So based on this resonance situation, and that formula, the questions are asked, right? And this is the last C. It has been asked in 1998 and 1999. So this is an homework from my side, right? You can ask, okay, some 3 to 4 sums I've given into the homework, right? And you can answer these questions into the, right, beneath the comment box, right? So this much, right, from the SHM, okay, this much from the SHM, right? The maximum part we tried to cover, right? Okay, so this was enough for the JEE NEET Crash course. The maximum part we tried to cover. Okay, so guys, thanks a lot. So this is Indrajeet Singh, right? This is Indrajeet Singh again. The last session of this champion series. You have shown us the support, right? You have shown us the support, right? Okay, till now, but the last part of the champion series, right? It is remaining. Okay, and that is waves, in which the most important superposition and the Doppler effect, the organ pipes, right, the Newton's formulas and everything, the most important stuff, right, from the exam point of view, we are going to discuss in that last session, right? So again, students, thanks for the love, and again I heartily apologize for the teaser, right? Okay, so this is Indrajeet Singh. Please don't mind for that, right? So this is Indrajeet Singh, right, signing off from the desk. Bye bye, Sat Sri Akal and Namaste from my side. Bye everyone. Stay at home, stay safe, stay healthy amidst the pandemic. Bye everyone.